So we're now ready to prove the main result. Basically, we'll move on to one direction of the main result. Basically, the number four, the full and reduced C-star algebra are the same. And to do that, we essentially just need to show that the left regular representation of from the full one to the reduced one is injective. And to see that, we actually just need a little bit more on the C-star algebra theory. So I'm going to talk about some background on this group algebra, and also we need to use some result about positive definite functions or positive linear functionals on C-star algebras. If you taken pure math A10 again, this is kind of obvious to you. You already have much more background on this, but if you haven't, just take some of these as facts, okay? So first of all, let's talk about the group algebra. So it's really a lot of in time when you study discrete groups, you will talk about this group algebra. So it basically consists of all these kind of the formal sums of alpha t times dot t. So here t is inside G, where this alpha t is going to be equal to 0 except for finitely many t. So you can really just think about it. You attach some number, multiply on your t, but you really can think about this as the C00 space inside of G. Okay, so you treat it as a function. If I ask you what's the value at t, you return the alpha of t, and alpha t are basically always 0 except for finitely many of them, and they really sit inside the L2 of the L1 space. Okay, so you see this is in the L1 of G, and they basically they're going to be dense, and often in times the C00 space is much easier to study. So you want to define certain map from C00 space first, and then you try to extend it to the entire the full C-star algebra, the reduced one. Okay, so you treat them really sitting inside your C-star algebra. All right, so let's talk about some map called the kind of the multiplier. Okay, so for every say phi from your group to the complex, and let's assume that your phi is in the L infinity of G. Okay, you can define the following. So you can define a map called the multiplier. So let's use this m phi first. Okay. So m phi is sitting from your group algebra, CG to CG. What it does is essentially just multiply, okay? So it takes a function f. So if your function f is a summation of alpha t dot t, you map it to the function where, so m phi of f essentially just multiplied by this phi, okay? So this is essentially the summation of alpha t, your phi of t dot t, okay? So you multiply each coefficient by phi of t, and as you can see, this phi, well, first of all, your alpha of t is mostly 0, so when you multiply, it's still mostly 0. Your phi is in L infinity, so if you treat the L1, think about the L1 norm, it doesn't really change your L1 norm too much, okay? So it just at most scale everything by the infinity norm of phi, okay? So your m phi really should be bounded on the L1 space. And because of that, you can imagine it's going to extend continuously to the, hopefully, to the C-star algebra, okay? So that's what we are going to prove. And you can do something similar for the reduced C-star algebra. So similarly, you say, let's call it f phi bar. You map it to the lambda of CG. Okay, so you think about the image of these group algebra under your left regular representation. And basically, I want to lift this map to a map on the reduced C-star algebra. So I define it basically using the same way. So let's say I'm a bar of some lambda f, okay, some f from CG, that I map it to the lambda of m of f, okay, and that's a pretty well-defined map, okay. So I want to show that first of all, these m, well, is only defined on kind of a dense subset of your C-star algebra. You treat the CG sitting inside the full C-star algebra, and of course the lambda CG inside the reduced one. They're going to be able to, you can extend them to the C-star algebra map. Okay, so here's the lemma. So in fact, if your phi is finite support, so it's finitely supported, and if it's positive definite, and if your phi of E is equal to 1, essentially just all the condition we saw from condition the number 3 we proved last time. All right, so then it allows you to extend. Okay, so then M of phi, if you think about it as the CG inside the full one, so that extends to a continuous map from C star, the full one, to itself. And also the M phi bar extends to a continuous map from the reduced one, okay, to itself. And both of them are going to have norm 1, okay, both have norm 1, so they're not just any extension, so they have norm 1. All right, so to prove that, I basically need several facts about the C-star algebra. I'm not going to prove them, so it's just some facts you need to accept, take it for granted. So let's say basically I need a few definitions. So first of all, if you have a positive linear functional, on a C-star algebra, A is essentially basically phi inside the dual space, and it's a linear functional. So that because your C-star algebra have the positive elements, so basically all those things with spectrum greater than or equal to 0, or think about them as all the AA star, then the positive linear functional will map these positive elements to positive values. Okay, for every A positive, this greater than or equal to 0 is in the sense of the C-star algebra being positive operator. Okay, then your phi of A is positive. Okay, so that's called a positive linear functional. And if phi is a positive linear functional, then its norm is actually very easy to compute. Okay, so to show its norm is actually just equals to the phi of the identity. And so if your phi of identity is equal to 1, then we call it a state. Okay, so a state is essentially just a positive linear functional, so that phi of E is equal to 1, okay? Or you can say phi of E equals 1, you can say it's uniform, or it's basically a norm 1 positive linear functional. And the states of the C-star algebra is really kind of determines your entire space, okay? That's kind of the quite important set. And if you study pure math A10, you probably heard of the GNS construction. You start from the state, you build some normally you build some kind of what we call it dilation, and you can also say that you can also compute a uniform norm using these states, basically. Okay, so so for every f, if you take the uniform norm, that's actually just the supremum of all these phi from state of your phi of f. Okay, so the uniform norm can be taken. It's bigger than all of these states. Okay. All right, so these are just some facts about C-star algebras. I'm not going to prove any of them. Okay, let's take them for granted. So let's use these facts to prove that I can extend phi into a positive a continuous map on the full C-star algebra. So we only need to do the full one. Okay, the reduced case is pretty similar. So if I consider my phi to be equals to a summation of some phi t, well, phi because it's a finite support positive function, so I can treat it as a kind of a linear span of the point mass measure. Okay, so t is inside some f. Okay, so f is contained in G is finite. Okay, that's the support of my positive definite function. So if you consider the m of this phi, you can really just multiply by each of combination of these delta t. So you can really treat it as a summation of the phi t of multiplication by delta t. Okay, it's basically linear combination. So let's just consider one particular delta t, okay? So for every t, let's consider m of delta t. Hopefully that's continuous. I can extend that first. So if I consider its uniform norm, well, what it does is that, well, m of delta t only multiply a 1 at the coordinate t, okay? So if you're, so the f you treat it as a function evaluate t, that map, well, that one got picked out, okay? So you end up with the uniform norm of this entry, okay? So you just take the t's coordinate, basically, that's all you left, because everything else is got multiplied by a 0. And the nice thing about this is that, well, this is a single entry, okay? This is a single entry. So first of all, the f of t is just a scalar. You can move it out. So this f of t. And then you take the uniform norm of the single entry t. Well, if you think about what happens to the single entry, well, the norm of the single entry is going to be the supremum of all the star representation of the single entry, which is, you think about it as a if you take a unitary representation, it's basically taking a unitary at this t, and then you take its operator norm and you take the supremum among all these unitary representations. But no matter which unitary you take, if you only take one of these unitaries, the norm is always equal to 1, okay? So it doesn't really matter which unitary representation you take, okay? So this norm is always equal to 1. So this norm is really easy to compute. This is f of t, okay? As you can probably notice, the difficulty if you just, instead of considering one of them, if you want to consider multiple of them, and you want to take the uniform norm of, say, even just the sum of two of these t, that's going to be much more difficult, okay? The norm of, say, the ut plus a us, that's going to be difficult to compute. But for one of them, the norm is always 1, okay? So that's gone. So basically, you only have f of t. So now if you let the following, if you consider the tau of f, I define a tau of f to be if you take the left regular representation of f, and you inner product with the delta e treated as a vector in the L2 space, okay, so you take an inner product. This one is a state, okay. So this tau is really positive. Well, because it's positive, it's basically you take a star representation, you take a vector inner product with a vector, so that's certainly positive. And because delta E is a unit vector, you see this is a state. And by the way, actually the states really, based on this proof, you can kind of see why the states are correspond to the positive definite functions. But in any case, okay, so you have a state. And let's just see where this f of t. In fact, you can just treat it as a tau of some kind of f. Okay, so let me show you how to do that. So if you say your f is a inside the L1, so let's say f is f of s times delta of s, delta s the point evaluation. So what is the lambda of f inner product with delta e? Well, the lambda of f is basically left translate of each of these delta e by delta s, and you multiply the corresponding f of s. So that's going to take, if you take on the delta e, well, each of these delta s is going to shift it by s, and then you multiply by the f of s. So this is the summation of fs delta s with delta e. And because these delta are orthonormal bases, so this delta t, t inside G, they're orthonormal bases for the little L2 space, okay? So when you take the inner product, well, you take the inner product with delta E, well, you only pick up what's the value at E, okay? So this is essentially a lot of these inner product are going to be 0. You only left with the function value at E, okay? So this is just really because the inner product of delta S with delta E is, well, let's not use Kronecker delta, let's just say it's 1 if S is equal to E and 0 otherwise, okay? So you pick up your function value at the identity. Well, you don't really just want the identity, you want the function value. And what happens if you want the function value at t, Okay, so here you see I want the f of t. Well, you just don't take the inner product with delta E, so you take the inner product with t. Okay, so the f of t is essentially just you can do the same trick. You say that's lambda f. Okay, I shift the delta E, I inner product with delta t, and then I will return my coordinate at f of t. Okay. So, but this one you can treat it as a lambda f delta E of a shift by t of my my delta E, this unit vector. Okay, and what you can do is you move the lambda to t to the other side. So this is lambda t inverse. T inverse is just really a function. You can really treat it as a shift by t inverse, or you can think about it as the function which is only one at t inverse coordinate. But in any case, this is you can rewrite it this way. And this is just the lambda of the left translation by t inverse of f, evaluate delta E inner product with delta E, or you can say this is equals to the state evaluate at t inverse of f. Okay. Well, why do we write it this way? Is because we know the states are going to be dominated by my universal norm. Okay, so the f of t is really just going to be equals to the state evaluate at this function. And that's going to be less than equals to the uniform norm, so T inverse F, the U norm, okay? Well, if you take a shift, the uniform norm, that doesn't really change, so that's clear. So this is just the F of the universal norm, okay? So in other words, what we can see is that my M of delta T is going to be a contraction, okay? So in other words, my M of delta T can be extended to a continuous map on the uniform C star, on the universal C star algebra, okay, on the C star U of G, okay. So for each one of them, I can do that. And here we're just using some little shortcut. So because your phi, your positive definite function, is a linear combination of these, and because each one of them can extend, and you take their finite linear combination, you have that phi can also be extended, or m phi can also be extended. And this m phi, because your phi is a positive definite function, so phi is positive, actually will imply the m phi is also positive. Okay. So the reason is just really, if you think about what happens to a positive, so you take an m phi of some positive elements, because your phi is only has finite support, so the m phi, when you take some say AA star inside your the universal C star algebra, the m phi will kill off a lot of the entries as long as it's no longer supported. So you really need to show that m phi is just positive on the group, on the positive elements of the group algebra. So your m phi, if you take something, let's say summation of say alpha s times alpha s bar of u s star and ut. So here I use the universal one. I treated them as an entry in the universal one. So here st are inside some finite support. Okay. So this one, I will have to map it. This is basically on each of these US star UT corresponds to the entry on S inverse of T. So this one will be mapped to the summation of phi of S inverse T of the alpha S bar alpha T of U of the S inverse T, okay? And to see this is going to be a positive value, okay, or a positive operator, well, what you can do is that you can treat them as, well, alpha are some kind of scalar. So you have that the U of the S inverse T, that's going to be a positive operator matrix. And you can multiply, you can take the pointwise product of the S inverse T. So here phi is a positive definite function, so you treat them as either multiplied by identity or, and from your assignment, you saw that how you do the entry-wise product of two positive definite operator matrix. They is still positive as long as they commute. So phi of st, they're essentially just scalar, so apparently they commute. So this is going to be positive as well, okay? So because of that, you take some alpha t, you do some kind of linear combination in this way. So here, s and t are inside some f. That's still going to be positive, okay? So that's why your n phi is still positive. So because it's a positive map between two C-star algebras, and you can use some deep theory about the C-star algebras, the M of phi, the norm, is essentially just its norm evaluated at identity, okay? And because it maps the identity to the identity, so this is basically just equals to the phi of E, okay? So this is phi of E, the norm of that, okay? Or you think about it as phi E dot E, okay? This is no other than the absolute value of phi of E, which is equals to 1, okay? Because you assume your phi E is equal to 1. But in any case, you see that this n phi, the norm is can be taken as its norm evaluated at the identity. Okay, so that give you the value 1. So it extends to your full C-star algebra this way.